This is on now.
See, this is TASI 1999. I guess this is the 25th anniversary. This was my TASI. Long, long yes. All the best wishes for your survival. By classic, you mean slowly falling apart.
Okay, I don't think we have anything else to announce, so let's go ahead with
All right, thank you. So can you hear me?
Is it on?
It's on, but yeah. All right, well, thank you. You must be exhausted. It's the last day of the week, and thank you for being here so early. All right, so today we'll finish up a little bit some of the interactions in the standard model, and then we'll look some at the standard model symmetries and the status of the standard model and what may lie beyond. So yesterday, so the standard model Lagrangian defined as the set of operators up to dimension 4 invariant under the gauge group and Lorentz is up there. We looked in detail at the Higgs, the middle part L Higgs, which gives mass to the gauge boson. So we got our beautiful mixing between the photon and the Z. Today we're going to start by now looking at the bottom piece, the Yukawa, which is the piece that you see couples the Higgs with the fermions, quark and lepton, and will give them mass. Once you go to the VEV here, it will give us the mass of the fermions and the interaction of the fermions with the physical Higgs particle. So let me, again, using that, the unitary gauge like that, we can now write L Yukawa in this form. So I'm just plugging in those things. So you see what happens. When I contract the doublet with the doublet, I pick up the lower component. So I'm going to be, remember, E left. For Q left, I pick up the lower component, which is D left, the D quark left. And for here, when I contract with phi tilde, the VEV is upstairs. So I pick up the up component of the doublet, okay? So that's what's going to happen. And so when I write it down, and remember, this notation, I wrote it only here, means that this YE, YD, and YU are matrices, 3 by 3 matrices in generation space, 1, 2, and 3. So here we have, if you plug it in, you get YE, ER, and then you get, so let me write it, there's a common factor which I'm writing at the very end, D bar L, I mean, you can guess what this is, the R plus U bar L, now I pick up that one, YU, UR, and the common factor is this one, V plus H over square root of 2. Plus, of course, there's the emission conjugate. Now you can immediately read off, I think there's a minus sign overall for the standard convention. You can immediately read off the mass matrix. I remember in the Dirac-Lagrangian, you have I slash minus psi bar M psi, right? So you read it out from here. So the mass of each fermion, so now F is going to denote each of these fermion field, is going to be its own Yukawa, where F, well, F is E, D, or U, times V, times the VEV. So this, as promised on day 1, links all the fermionic masses to one scale, the V, the electroweak scale. However, these are matrices, so they're not diagonal in general, unless you engineer things in a certain way. And so we have to diagonalize them. So there's a bunch of ways to do it. So first I want to go back and look at the gauge part of the Lagrangian, right? The gauge part, I wrote it painfully with all this reducible representation of the fermion. It's that part has a big flavor symmetry, unitary symmetry, which sometimes called U3 to the 5th. So let's explain the 3 and the 5. The 3 is because I can rotate each of the fermionic multiplet in family 1, 2, 3, independent. And the 5 is because I can do it 5 times. I can do it independently for the left-handed lepton, the left-handed quark, right-handed. So in other words, that Lagrangian remains invariant if I do independent unitary rotation on each of the 3 by 3 rotation in each of these multiplet. That means I have a lot of freedom to put these matrices almost in diagonal form, right? I can use that symmetry to rotate things, to put the Yukawas in almost diagonal form, right? But it's not, I can't quite do it fully, and I'll explain why. There's one residual thing that we have to take care of. So, but in principle, even if you didn't know about this U3 to the 5th symmetry, so what do? How do you diagonalize a general complex matrix? There is a way to diagonalize with bi-unitary transformation on both sides. Okay, so we're going to write basically YF. I can always write it as YFL because I put the left field in this convention on the left. So it's going to be some V 3 by 3 FL on the left, then YF diagonal VFR on the right. Okay? For F, at this point, F, I can write E, U, and D. In other words, and now remember this was multiplying fermion field, so I can go to the mass eigenfields, which I can always define as F. Let's see, let's do it this way. Left, right, prime as V, F left, or right times the fermion field, the original fermion field, left, right, okay? If I write things in terms of this primed field, the mass matrices are going to be diagonal. And you see, once I diagonalize the mass matrices, also the coupling to the Higgs is diagonal because there was an overall factor. So we get an important result. Now forget about the primed fields. I can write the Lagrangian Ly as minus summation over the F equal E, U, and D. MF, F bar F, 1 plus H of X over square root of 2, V. So now I switch to the, what is F? F is the regular Dirac field, F left plus F right. That's a definition. So, well-known result. Well, let's look at it and discuss it. So once you diagonalize, the Higgs coupling to the fermions are proportional to the Yukawa. So at fixed VEV, they're proportional to the masses of the fermions. And the other important thing is that they're family diagonal. So there's no flavor-changing Higgs-mediated current. I cannot go from a muon to an electron or a tau or a strange to a D with this coupling, okay? This is important. All right, so that's that. Now, there's one final piece before and I'm gonna use, sorry, so let's stare at this one too. It's important, it will be important at some point. Now we have the mass eigenstates for the gauge boson. We have the mass eigenstates for the fermions. We're now going to write the all-important fermion gauge interaction. Basically, we need to express those psi bar, the slash psi, in terms of the mass eigenstates. And so I'm going to write it and explain the notation. So fermion gauge is, so there's a lot of term once you write it explicitly, but psi left and right. And for me, so psi left, by psi left I mean Q left and L left, the doublets, and psi right, let me write it here, sorry, is going to be the right-handed lepton, ER, UR, and DR. So in this notation, I get, let's look. So this first line is going to be the charge current, so the interaction with the W plus and minus. So you get psi L. And for this line, I'm going to, let me first write it down, then I'll add the family indices as well. Gamma mu, tau plus, T plus. What is T plus, do you remember, in terms of sigma matrices? T1 plus IT2, great. And then you get, of course, it's conjugate. And let's add the indices. So this is the charge current. Indices are, in principle, alpha, and we'll see what happened in a moment. This is the charge current. Then there's the neutral current, with weak neutral current, which is the coupling with the Z. And this has the following form. Sorry, I should put a big parenthesis here and a smaller parenthesis here. So now we're going to have psi bar L alpha, gamma mu, so they're vector, but also they're chiral current, as you expect. Now there's a T3 generator minus sine squared theta times the charge generator, okay? This is how the left-handed things coupled to the Z boson. And then I have sine squared theta, the charge generator, and then the right-handed R alpha, and then the Z mu field out here. Sorry, and there's the charge is inside. In this notation, in this compact notation, charge, it's easier to think this way. And then the electromagnetic, plus E. Now it's going to be, because it's a vector-like, well, let's write it, psi bar L, gamma mu psi L, plus psi bar R, gamma mu psi R, A mu. And the Q's are inside. Okay? In this notation, the T3, of course, acts on the doublet. The Q acts both on doublet and the singlet. Let's look at what happens when we now apply this. We want to write the original field in terms of the primed, the mass eigenstate. And we don't have to work much for the neutral current. Let's start with the neutral current, right? So the neutral current, you see that when you act with unitary matrices in family space, right, they don't talk to the gauge indices. This is where it starts being a little, you can get dizzy very easily with indices and stuff. Those V matrices do not talk to the gauge quantum number in family, so they go through. Okay, V dagger V is the identity. Those were unitary. Same here, same here. So there's no, so let's write the results down here. No 3-level FC and C means flavor-changing neutral current. The neutral currents are all flavor diagonal, and we also learned that the Higgs coupling neutral current are diagonal. Let's now look at the charge current. So the charge current, first let's look at the leptons. I have to rotate, so let's think about psi L as really, what is psi L for the leptons? So I have to do this unitary rotation in family space to both to the right and left charged leptons. The right, I can do it. It's part of that U3 to the 5th. The left, I can also do it freely. I rotate the full doublet, and it does nothing to the neutrino. It's just a field redefinition of the neutrino. There's no other interaction that involves the new left. So they also go through. Basically, once I diagonalize, there's nothing that, right? Because I have the same rotation here. Psi left on the left lens. So they go through, and there's no flavor changing in the charge current interaction. So this is very important. This vertex with the W is going to really involve E bar L alpha, gamma mu, nu L alpha. This we call, this alpha is 1, we call it the electron, and this we call the electron neutrino, and so on, mu neutrino. So it's very important. So because now we can, the charge current, for the leptons, we can conclude that I can make independent U1 rotation on each of the families, and this is a symmetry. This is because this is diagonal. This is all those phases goes through. I never have a E mu here, never have an electron here talking to a mu neutrino. So lepton numbers are conserved. That's an important thing that, so L alpha are good symmetries. It's great. The final thing, charge current quarks. Here is where things don't quite work out. You can imagine now why. So let's see, because on the quarks, QL alpha is really UL alpha, DL alpha. The charge current we want to mix, right? It's U bar L, DL. And when I do, so there's one thing, unless this rotation that I have to make here for the up and down quark matrices, unless they're the same, the left-handed part is the same, then the charge current interaction will not preserve individual quark numbers. So what happens is that let's take one of these examples. So psi bar alpha, so QL bar alpha, gamma mu T plus QL alpha becomes U bar alpha, gamma mu DL alpha. So when I try to rotate in terms of the things, I get, and if you take care of those indices, I think you end up with this. You get this matrix, which is V, U, L, V, D, L in the notation on the leftmost board. Gamma mu D, L prime. And now I suppress the indices, but I can write alpha, alpha, beta, beta. So there's a matrix in here that mixes the up to the down quark. So this matrix is called the Kabibo-Kobayashi-Maskawa, VCKM. And since it's the product of a matrix with another unitary times a unitary dagger, this is also unitary, sorry. So VCKM is 1. But what we learn here is that individual quark number is not conserved. So if I now do, so let me write, again, if you have never seen, let me write it explicitly. So on the first row, you have VUD, VUS, VUB. Second, you have VCD, the charm, VCS, VCD. Third one, you have UCT, TD, VTS, VTB. Okay? So a W can mix. So the W coupling now, you have U, I, D, J. And here the coupling has a VIJ. times the universal gauge coupling, all right? So it's very distinctive prediction and testable things. Because this is a unitary matrix, there will be the rows and columns are orthonormal vectors. So they're two of them are orthogonal, but the same, each one of them has a norm 1. So we'll see how we can test some of these things. Then, we want that one visible. The final thing I wanted to discuss before, maybe this is, where do I want to do it? Let's start. I'll use one of these boards. Let's count the parameters in the CKM matrix, right? So, and this is also left, the details are left as an exercise. So it's a 3x3 unitary matrix. How many, in principle, how many free parameters do I have? It's a U3 matrix. I would have 9. SU3 would be 8, n squared minus 1, and 1, the 9th is the overall phase of the U3, right? So I have 9. You can easily convince yourself of these 9. 3 are mixing angle, and I see this if I go back to real matrices. So 3 are so O3 has 3 mixing, 3 mixing angle, 3 thetas, let's call it, plus 6 phases. Now I still have a freedom to get rid of a bunch of these phases because I can redefine the phase of my 6 quark, the up type and the down type quark. I can redefine a phase. The overall phase goes through, so I can get rid of 5 phases. So you can check, this is very simple matrix things. There's going to be 3 mixing angles, 3 in 1 phase. And therefore, remember when you have complex coupling, this already should remind you there may be some breaking of discrete symmetries like CP. And now let's explicitly check that. So the exercise I'd like you to do is that do this counting for the 3x3 mixing, and also do the same counting for a 2x2 mix, if you had 2 generations, not 3, right? So in the 60s, it was, well, almost 2 generations. The charm quark was not known yet, but the idea was that you had 2 generations, and then in, I believe in 73, Kobayashi Masukawa generalized to 3, but this simple going from 2 to 3 means that there is a irreducible phase, and therefore CP violation. So the exercise is to show that in the 2x2 case, you can rotate away all the phases, okay? So that, and therefore, now the important implication of this is that now let's write down explicitly this charge current Lagrangian and act with a CP transformation on it and check whether this is goes into itself. So there's an overall factor which are not, well, let's put it, G, Vij, there's going to be a W mu plus, and then get you L gamma mu dLj, plus, remember I have to always put the admission conjugate, G is, we take it real, Vij star, this is a parameter, just under admission conjugation, I don't change the indices, I just take the complex conjugate. W mu becomes plus, become minus, and these things become d bar Lj, so I have to take the admission conjugate of this, so J goes on that side, you Li. So what happens under a CP? Under a CP transformation, again, so the coupling don't change, but I have to act on the fields. So the fields go into their conjugate, and so what you get G Vij, so this does not change. W mu goes into, it's minus. This one goes into Lj. It's the complex conjugate, the conjugate current. Star, I'm copying this, then this becomes W mu plus U bar Li gamma mu dLj. Okay, let's see. So it's almost invariant. What do I have to do to enforce that the Lagrangian goes into itself up to, well, in this case, really into itself? What's the condition I have to impose? So this term looks a lot like this one, right? Look at the diagonal, except there's a complex conjugate here in the Vij. So if Vij, so these are in correspondence, and I'm not going to draw the other arrow, otherwise it becomes too busy. But the condition is that if Vij is real, I get CP invariance. If Vij is complex, CP is violated. Okay, so this is this exercise was worth a Nobel Prize. Okay, so the final thing before we switch to the slides is looking at the low energy. So remember, we started with the low energy. That's how we kind of guessed the gauge group. Let's now go back. Now we have the full standard model. What would be the low energy realization? Basically, you integrate out, and you can. This now we can do. This is a effective field theory where you know both the high energy theory and the low energy theory. You can do the matching order, and it's perturbative. It's a weakly interacting theory, so you can do the matching in perturbation theory to any order that you have stamina for. We're going to do it at 3 level. So basically, the idea is you have the current. This can be W or Z, and these are the fermionic current. So the low energy Lagrangian looks something like this. Now we can do it for both the charge current and the neutral current, because we know we have the Z. They look, let me, a little bit of definition again. This should be by now J mu, the current carry the generation, an index that has to do with the generator. Psi bar left, gamma mu, T, I, psi left, right? So that's a notation for the currents. And psi left are Q left and and L left. So G Fermi, J plus, so now these are 4 vector, J plus dot J minus. They should be somewhere there. Current, the current is whatever multiplies W, right? I mean, it's this one. Then you get something called the rho parameter. I will define it in a moment. J3 minus sine squared theta J electromagnetic, the good old electromagnetic current, dotted into itself, right? J3 minus sine squared theta J electromagnetic. And rho, so rho is defined as mw squared over mz squared cos squared theta, the weak mixing angle. So at 3 level, as we saw yesterday, is 1. But in general, could get radiative correction, could be different from 1. So, so this is the piece that we get by integrating out at 3 level the W. This is the piece you get by integrating out the Z boson, okay? From this, all the low energy physics, so there's a lot of physics in this one. So there's, for example, muon decay, from which we extract the highest precision G Fermi. There's all quark semi-leptonic decay, because this could be a quark current, this could be a lepton current, and so on. They're purely leptonic, purely quark, and semi-leptonic. A lot of stuff in that innocuous looking Hamiltonian. There's one thing that I'll mention later, so I can write this thing as J1.J1 plus J2.J2. Look what happens. If rho is 1 and I forget the mixing angle, this becomes the dot product of a triplet of current. So it's a remnant of some symmetry. And that's called the custodial symmetry. We'll say a few words about that in the next few minutes. And I want to leave you with writing explicitly this current and pointing out some names, some buzzwords that you'll hear, I'm sure you've heard in the literature. So this charge current displays some universality conditions. So delta AB L alpha. So because of this delta function, the charge current weak interaction involving leptons, they don't depend on the fact whether you're at E or mu or a tau. This is called lepton universality. And then you have a similar thing. Quark universality or quark-lepton universality is also valid up to this unitary rotation, the Cabibbo, the CKM matrix. And this, unfortunately, I'm the right bottom corner. But so now you have V alpha beta dl beta. So this is not a delta function, but remember there's a universal coupling in front, G Fermi. Its quark and lepton universality holds up to this unitary rotation, and so we can check. Basically, the strength of the coupling is shared between up, down. So for example, it's V in the first row, you get VUD square plus VOS square plus VUB squared. And sorry about the indices here, you have to 1. So this unitary condition is essentially quark-lepton universality. It's a low energy footprint of the fact that at high energy, the currents just talk to the W with a universal coupling. All right, so let's now switch to the slides. While we do the technical switch, there's one final thing I wanted to mention, is that.
So you still want it on the two-side balloons?
Yes. So because I may use to add some comments at the middle board. One thing that we did not cover at all was the standard model at loop level, at the quantum level. This is all so far. I wanted to discuss the 3-level structure. The quantum level, besides the Feynman rule, well, on the perturbative side, you have to, as we saw the first day, you have to work a little harder with gauge fixing and so on. But there's nothing deeper than that. One important deep thing to check the consistency at the loop level is to check that there's anomaly cancellation, right? That none of the gauge symmetries are anomalous. And this can be checked. And it works out and actually provides, interestingly, a link between quarks and leptons. So you need equal number of generation of quarks and leptons. And with those specific and admittedly odd hypercharge, little weird hypercharge assignments. Otherwise, things don't work. So people are excited that this is a link towards charge quantization. But that's what it is, right? So right, now what I wanted to do now, I wanted to pause and look at the symmetries of the standard model. And go through that. Obviously, so the gauge symmetry that we started with was the thing we wanted to build our theory on. Is manifest for color, and it's hidden, as we saw, through the Higgs mechanism in SU2 cross U1. So that's. What about the global internal symmetries? All right, so remember there was now it's unfortunately hidden under there. There was a huge global symmetry of the pure kinetic part, gauge kinetic part, U3 to the 5th. That is broken, fortunately, by Yukawa coupling. Otherwise, we would have no notion of what is first generation, second generation, third generation. So the Yukawa breaks the non-abelian factor badly. But as we saw through those exercises, by looking at the coupling of gauge to currents, a few U1 factors survive. So the total baryon number, so if I rephase all the quarks, irrespective of whether they're left, right, e to the I, let's say alpha baryon over 3, this is a good symmetry, and that's a baryon number conservation. Similarly, as we saw, if I do the same for each individual lepton number, Le, L mu, L tau, I get the same. Therefore, the total number is also conserved. Great. However, there is an anomaly for baryon and lepton number. The total baryon and total lepton number are not conserved at the quantum level. However, it turns out that the breaking, when you write down the anomaly, anomalous non-conservation of the current, turns out the breaking is the same for them. So B minus L is conserved. B plus L is violated in the standard model. Do we need to worry about this? Is there any reason to worry about the stability of the protons in our body, for example? It turns out, I don't have time, unfortunately, to go into detail, but the reason is no for two reasons. One is that at 0 temperature, this process is very suppressed. It's a tunneling, and so it's important at high temperature in the early universe, so it's crucial. Many models of baryogenesis, including leptogenesis, rely on this. The other thing is that the selection rule wouldn't work. Is that delta L equal delta B equal 3 or multiples of 3. So it's, while we are at global symmetries, there's a bunch of approximate global symmetries that survive, right? Let's first do the thing that's most tangible. There are symmetries, near symmetries of the quark mass matrix. When you put it in the diagonal form, this is the famous the MS and so on. So if M up and M down were the same, this is an SU2 symmetry in the quark sector, and this is the isospin symmetry that Heisenberg saw in nuclei. So this is, if I put the strange quark on the same level, is the SU3 symmetry of Gell-Mann and so on. And of course, they're broken. Both explicitly, but and also the chiral version of them is broken also spontaneously, and that's why the pions and kaons are the lightest hadrons in the spectrum. There's also here in this footnote something I call the custodial symmetry, and that would be the thing responsible for the draw parameter close to 1. That's a symmetry that you can most easily see in the Higgs. You start in the Higgs sector. This is the famous O4 being broken to O3, but it's most easily seen if you write the Higgs field in this form. If I tilde a vector, so which basically is, so phi is phi plus phi 0 star minus phi minus. You can rewrite the Higgs potential in terms of trace of sigma dagger sigma, as well as the kinetic term of the Higgs Lagrangian. And so you see the O4 symmetry that you have if you write these in terms of real fields becomes an SU2 cross SU2. So basically, the sigma field, you can make independent rotation of a G left, sigma, G right dagger with arbitrary, so G left and G right are independent SU2 matrices. So this is a global symmetry of the Higgs potential. The only thing that breaks, in the end, this symmetry in the Higgs sector is the G prime, the hypercharge, because these two things, because they're the conjugate of each other, they pick up a relative minus sign under hypercharge. So, so this symmetry, when the Higgs acquires a VEV, So when this becomes V times the identity, is broken to the vector subgroup where the GL is equal to GR, because it still goes through. It's still a symmetry of the vacuum. And so this residual SU2 is called the custodial symmetry. And the important thing to keep in mind is that it's broken by G prime, so the U1 assignment, and you can see because of this, the column pick up a relative minus sign. And if you try to extend it to the quark sector, and you're tempted to put it, yeah, it's a valid extension, is to put UR and DR as a doublet under this SU2R. Then the things that breaks it is the up type Yukawa being different from the down type Yukawa. If they were the same, that would also be a good symmetry of the quark sector. So it's basically corrections to the rho parameter go like a radiative correction, so perturbative in G, and then they go like Yukawa top minus Yukawa bottom. So that's an important symmetry to be present. Since it's in the data, right? This rho parameter is close to 1. Any extension of the standard model should know about this, or should preserve. So enough for global symmetries, discrete symmetries. So parity and charge conjugation, we saw they're maximally violated by the fact that the theory is chiral. Maximally violated means that the weak interaction, so they say a left-handed electron feels the weak interaction, a left-handed positron does not talk to the W boson. It's maximal violation of charge conjugation. And a left-handed electron talks to the W boson, a right-handed electron does not talk to the W boson in the massless limit, so it's maximal parity violation. CP, or time reversal, again, we saw this in this weak sector, the CKM phase breaks it. And that leads, as we'll see in a moment, to a very specific pattern of CP violation. And then in principle, we have the electroweak, the non-abelian theta terms, which I'm going to write here. Normally, we talk about the QCD theta term, but actually, you could have also theta QCD. There's usually the normalization is G squared over 32 pi squared, G dual. But you also could have a theta electroweak. So G, this is G strong, this is G. W tilde. So it turns out that for the electroweak theta term, making some the anomalies somehow save us. You can make a chiral rotation, a rotation that involves, so a field redefinition that looks like a total baryon plus lepton number. And that, as we said, produces an anomaly, anomalous term in the Lagrangian. So the transformation induces a term that looks like this. And so we can eliminate this by making a field redefinition. If you make that same type, then you can play with field redefinition on the quarks, axial field redefinition on the quarks. But unfortunately, what you do, you end up either, if you want to you can get rid of the theta term here, but you end up with complex quark masses. So there's no free lunch there. It's either here. So in fact, the physical combination is some theta bar that goes like, let's call it theta gluon, theta GG dual, the piece that you would start with in your Lagrangian. And then you have something that goes like basically the phases of the quark masses. So you write it in this form. So it's the argument of the determinant of M quark. It's simply the fact that once you diagonalize the quark masses, there are phases on the diagonal. You take the product of those phases. That's the argument of the determinant. So that's the physical thing. And the fact that this, we know experimentally from the absence of an EDM of the neutron that this is less than 10 to minus 10, that's puzzling. goes sort of against the ideas of EFT of writing all the terms you want based on on symmetries, and has led to many theoretical developments. Okay, so those are the symmetries. I want to say something about accidental symmetries. So some of these global symmetries, like baryon and lepton number, lepton family, are not an input they were not an input, right? They just came as a consequence of, our input was, here's the field content, here's the gauge symmetry and Lorentz invariance, write all the operator you can. And that baryon number came out, lepton family came out. In that sense, those are called accidental symmetries. If you, in fact, you expect that when you go to higher order, higher dimensional operator, you're going to break them. They were not a requirement in your theory. And sure enough, we'll see an example of accidental symmetry being broken by higher dimensional operators. Let's see. So, yeah, this is a comment. These approximate symmetries or symmetries broken in a very specific way are one of the prime places where we can look for non-standard physics, because they're a very specific pattern of the standard model. Status. Okay, I have way too many slides. You can take a look. But I just want to give you a quick idea. By doing loop corrections and looking at all the electroweak precision, probes involving the Z boson, the W boson, both at high energy, directly in their decays, and at low energy, in computing quantum loops, there's a consistency at the roughly per mil level. So it's kind of astonishing. There's a few tensions, 2 to 3 tension. In this particular plot, what you're seeing is the Higgs mass versus the top quark mass. Before the Higgs discovery, the standard model precision tests were pointing to this, well, this region here. Sure enough, the Higgs came a little bit on the edge, but basically you had a pretty good idea of where the Higgs would be if the standard model is the correct theory. And this is one example of the power of these indirect probes. Flavor and CP evaluation, this is also another astonishing story. So as we discussed, there's no 3-level flavor change in neutral current. At 3-level, there's only this charge current that can change the flavor. You can study this CKM matrix. It has this data points to the fact that this is very hierarchical. The identity and then corrections controlled by this small parameter lambda, the Cabibbo angle essentially, 2.25. And then so you see lambda, lambda squared, lambda cube. And then there are phases of order 1 and A of order 1. You can study this in many, many processes. And I'm not going to go into detail, but I just want to show you the consistency. This is the status from the CKM Fitter collaboration. There's a lot of data from B meson decay, K meson decay. And in this parameterization, the Wolfenstein, there's 4 parameters, lambda, A, rho, and eta. If you project it on the rho and eta plane, this is how it look like. The triangle is really a condition of orthogonality of 2 of the rows of the CKM matrix. And the fact that all these constraints from meet at the apex there of the triangle is highly non-trivial. I mean, when I was a grad student, there was a big hope that the triangle would not close. This unitarity condition would not close, but it closes to an astonishing level. This, again, is a strong constraint on model building beyond the standard model. This is the one thing I've been involved in playing with, is the Cabibbo universality test. Is another test of the CKM unitarity, but now it's not the orthogonality of 2 rows, it's the fact that the first row has norm 1, right? And so you can extract to high precision VUS and VUD. You plot them in this, so this is the circle, which the curvature is very large, so you see the unitarity circle would be a giant thing. And all the constraints do not meet on the circle. There's some tension there, and there's a lot of interesting work. I mean, the name of the game here, you have to both predict these things in the standard model with high precision, sub-percent. So it means you have to do higher loop calculation. And then you have to come up, once you see something, you have to come up with possible explanations that are not obviously ruled out by other things. Yeah? So it's, right. The Higgs boson, it's another, so I'm just walking you through the status of the standard model, both at low energy. Now we're going to go to higher energy. Higgs boson, very hot topic. I stole these plots from this CMS 10 years anniversary from the Higgs discovery paper. It's actually a very nice summary. The Higgs now, we went through yesterday, right, through all the couplings, right? How it talks to the fermions, how it talks to the gauge bosons. And so turns out the dominant production mechanism at the LHC is gluon-gluon fusion. This vector boson fusion is the next dominant, and so on. And there's a bunch of decay modes, vector-vector, gamma-gamma, so where it was discovered, fermion-antifermion, and so on. And of course, if you remember, the coupling is the strongest to the highest mass particle, all right? And so we'll see in the next slide where are we in testing the precision, the prediction. The thing that it's for the future, because the cross-section is suppressed, is this pair production, which is now sensitive to the triple Higgs coupling. This has not been observed yet, so it's a big thing for the next phase of LHC. So does this specific pattern hold up? And the answer is yes. So it's, again, particle mass, yes?
Sorry, on the last slide, in the
Yes. So V is a vector boson. So V, and of course it can be on shell only for gamma gamma. Otherwise it's a V star. I think that's you can have Z virtual, right? Or two virtual Z, and then they go into leptons. Yeah, yeah, that's how they. So here's this test. Okay, look at the log scale. So it's been seen all the way down to the muon. So WZ top of the heavy particle. Here's the deviation. So if you rescale them, and so take the ratio to the standard model, you see that it's the prediction is at a few percent level for the heavy particle. Here, because it's a lower statistics, it can be at the 10% level. So there's some wiggle room, but the pattern, when you look at the log scale, seems, again, it's a strong constraint on model building beyond the standard model. Better reproduce this prediction of the simplest thing that you can write down. This is a cute stuff. It looks like we live in a metastable universe. The vacuum is metastable. I encourage you to read, or we can talk about this later. But so these authors, and there's an area again of active things. You can look. First of all, this is a nice summary of all running couplings in the standard model, right? This is the left plot as a function of the normalization scale. You see the Higgs mass grows very mildly, logarithmically. The important thing is this lambda, the Higgs self-coupling, that it's controlled by the phi to the fourth theory, this little lambda square, so it grows. This would be wants to go to a Landau pole, it blows up. But there's a negative contribution from top quark loops. And so depending on the actual value of the top quark mass and the lambda, you can end up in various situations. So on the right side here, so the very large Higgs mass, you would very quickly go to the Landau pole. I mean, it would become very strong coupling, non-perturbativity, this is the thing. For very light, so moving on one line, a fixed Higgs mass, top mass, when this becomes very small, so light Higgs mass, then the top take over, and it wants to make it negative very quickly. And so you have this region, and you go into the instability region. When this quartic coupling is negative, you have another minimum at very high, large field. So it seems like, so it's barely visible. Here's the point where we live, And we are in this wedge of metastability, and it's very curious. I have nothing to say. I'm amazed by this, but it's a fact. So now BSM in 5 minutes. 20 minutes? Oh, sorry, 20 minutes. Yeah. Why am I rushing? Yeah, relax. So I hope. So this is. I wanted to give you a snapshot. So the standard model is working unreasonably well. Okay, that's my take. But also, it fails spectacularly on other things, right? Why do we want to think about the standard model? Beyond the standard model, there is very empirical evidence that, I mean, that picture on the right, we understand nothing based on the standard model. We don't understand the very existence of matter over entanglement stars. We don't understand the dark matter, of course, let alone dark energy. Not even in the minimal definition that we've been using with the minimal field content, we don't have a way to give neutrinos a mass. So one has to deal with that. And there's also more theoretical. So this is empirical thing. I resonate a lot with the empirical reasons why we need new physics. There's a lot of theoretical reason as well. And they go under various names. Higgs naturalness, this, which I want to say, it's really the sensitivity. The quadratic divergences don't exist. They're a regulator-dependent statement. It's more the sensitivity, if you really want to express the renormalized couplings, like renormalized mass, in terms of high energy parameters, there's this jump. Again, as an effective field theorist, there's nothing wrong with that, I would say. As long as your physics stays whatever it has to be at low energy, there's nothing deeply wrong with that. But some people find it big problem, so let's put it there. Then there's a coupling unification, right? So if you look at under this, I would say, you've seen the charge assignments, right? It's ugly, right? It looks like, really screams for a unified, more unified. This looks like the fragment after breaking and breaking symmetries and so on. So there are ways, there are ideas, of course, the grand unified theories, and that's very elegant, but they also run into problems because you have to test them. Origin of flavor, no idea. Strong CP problem, are these pointers to new physics? So you take your pick, but taken together, I think this is a strong indication that there has to be something else. The standard model is incomplete, it's some low energy. And then you can ask the question where this new physics could be. And again, this is a cartoonish version, two-dimensional, one mass scale, one coupling. We sort of have control at relatively low mass with direct access and relatively large coupling. But even at low mass, if you make the coupling of a particle extremely small, you start moving into this dark sector, and we don't know if there's anything there. We can probe. Or the classic guts, UV completions, they live up here. But anywhere outside of this cartoonish boundary could do. So we look for it everywhere. High energy, low energy. And I think EFT, you will see in the rest of the TASI, a lot of application ideas, concrete ideas for how to explore this unexplored region. Some of them will rely on effective field theory, but my claim is that any of them, you can think of them in the EFT frame. It's a framework that you can think of, and any concrete realization of new physics, you can bring it down to EFTs. So the popular thing that you'll hear about, you already heard about, is this: if the new physics is in UV, we have something called the standard model EFT. Basically, the idea is continue what we've done so far. Build your Lorentz engage invariant operators of dimension greater than 4, though. Don't stop at 4. With the standard model fields and the standard model gauge symmetry. This makes some assumption. It's model independent, but it makes some assumption, very important assumption. it assumes that there's no other light degrees of freedom. We got the right thing, and we got the right symmetries. We also know it assumes that, for example, the observed Higgs is part of a doublet under SU2. It's an assumption. And then the expansion, as in any EFT, is electroweak scale over the lambda, the new physics scale, or energy over lambda. Sorry, this should be E over lambda. And then you write down, it was pioneered by Weinberg, 79. Turns out that there's only one operator at dimension 5, and it violates lepton number. There goes your accidental symmetry. It's gone already at dimension 5. At higher dimension 6, you have all sorts of violation. Baryon number violation, lepton family violation, tons of sources of CP violation, flavor change in neutral current. So a lot of things happen at dimension 6. You have a rich structure. This effective theory, I find it very useful because on one hand, it can relate to UV theory, any UV theory with a matching calculation. It's a matching calculation away from SMEFT. And also it allows us to go all the way down to connect to experiment. In particular, I'm interested in low energy experiments, so I'm interested in going all the way down to hadrons and nuclei, and so on this side too. So it's SMEFT. We'll see the dimension 5 example in a moment, but I want to say for completeness, it's not the only game in town when you're thinking about high energy extension. You can change a particle, add particles, or change the way symmetries are realized. So if I add our friend from yesterday, the right-handed neutrino, which is a singlet under everything, this framework is called NewsMEFT. There's also something called HEFT, Higgs effective theory. It's in this HEFT, what you change the way symmetries are realized. You basically say that we know, because we've seen all we can take from this, the assumption is data tell us that we have spontaneously broken theory, so we need to put the Goldstone modes there, and you put them like we do in QCD with pions. But the Higgs could be now a singlet under this symmetry. In fact, you put the Higgs, the physical Higgs that's been observed as a singlet, and you construct your EFT. You have a lot more freedom there because it's less constrained. You can write a more general Higgs potential and so on. And so it will be interesting to compare with data, but and think. Dark sectors. So it turns out also dark sectors, you can think of them, well, the way we talk, our world talks to dark sector, you can also think of it in an EFT way. I'm sure you've heard the word portals. Portals are really in the EFT sense. So the idea is that there's this dark sector, and there has something that communicates between the standard model and the dark sector. And again, we remain agnostic about the mass scale. It could be some large scale lambda. But there are a few interactions that are unsuppressed by dimensionality, unsuppressed by any scale lambda. And those are the portals. Those correspond to the lowest dimensional standard model singlet operator. Remember, the dark sector is by definition singlet under standard model. So let's take the example of this vector portal, the dark photon or whatever, vector portal. So we know B mu nu is a singlet. So the U1 B mu nu is a singlet under standard model, doesn't transform. If I couple it in Lorentz invariant way to a singlet from the dark sector, there it is. I have my portal. You can think of this as arising from, for example, some heavy particle that is charged under both. This is A, this is B, and this is our A prime. And there's some heavy stuff, and this loop does not decouple, does not go like 1 over the lambda, so this generates this. The Higgs sector, you can write down again, H dagger H is an invariant of dimension 2. I can couple it to a singlet or a singlet squared. This is so-called Higgs portal. There's a neutrino portal, very important. So L bar H, sorry, H is now what I've been calling phi, the Higgs field doublet in this notation. This is again an invariant because the hypercharges work out and the SU2 indices work out. I add a right-handed fermionic degree of freedom, which is sterile under, so it's neutral under all the charges. That's what I've been calling right-handed neutrino, nu R. And this is a Yukawa interaction. And this is the so-called neutrino portal. This is another perfectly valid extension. And you can then add mass terms to for the right-handed neutrino and study the physics as a function of this right-handed mass. Axion and so on. I mean, I'm not going to. Axion, the lowest dimensional operator involved already started dimension 5, but there's a very interesting phenomenology as well with axions. I want to conclude with the neutrino mass because it's a very concrete thing, and we see what are the most economical way to accommodate neutrino mass. Again, the discussion is dictated by symmetry. As you probably notice, most of what I said is dictated by symmetry. Lorentz, you ask yourself, how do we write down mass term for a fermion consistent with Lorentz? Since a neutral, normally we write the left option, right? Dirac, because we also want to preserve some charges for charged fields. In the case of a neutral particle, which is really neutral under, and there's no charge, you can't write any charge, associate any charge with that. You have this option here with which is a psi instead of psi star psi. It's and you build it with the charge conjugation matrix there to make it Lorentz invariant. It work out. That's a so-called Majorana mass term. However, you see immediately there's already a problem here. If psi is our neutrino field, on the left side of the Dirac option, I need to add a new field, nu R, which was not required by weak interaction. It doesn't seem to participate in the weak interaction. On the right side, that thing involves the isospin plus 1/2 component of a doublet by itself is not gauge invariant. So SU2 invariance requires new degrees of freedom. Of course, yeah, on the left side, we know so the thing on the left here is just the neutrino portal that I just described. You can write a renormalizable Yukawa interaction, dimension 4 Yukawa. For the Majorana thing, there's, again, many options. One is, again, most economical would be start with the neutrino portal, but then go back to what I said here. Since that nu R doesn't carry any charge, let me write. I can add something like this, and it does not violate anything. It's in accordance with our symmetry principle. It doesn't violate the gauge symmetries. It violates lepton number, right? But we said just write all the things that are Lorentz and gauge invariant. So that's, if you do that, then you can generate, and the nu R, that M is heavy, you can integrate out this heavy neutrino, and you end up with a dimension 5 operator. This Weinberg dimension 5, which we'll see in a moment in greater details beyond cartoons. But sticking still with cartoons, there are many other ways. We may say no minimal ways of generating a Majorana mass through, for example, the exchange of a triplet Higgs, and then the triplet Higgs here talks to our regular Higgs, and it acquires a VEV, and it becomes, again, a Majorana mass. All these things on the right, if the mass scales of these new degrees of freedom are sufficiently high, they look from our perspective as a dimension 5 operator at low energy, the Weinberg operator. And again, these two options, they seem, they're what they are, but they're distinguished by global symmetries. They both violate individual family numbers, so they would both be perfectly fine in explaining the neutrino oscillations. But the Dirac option, you can still assign some lepton number, total lepton charge. For the Majorana, no. It violates lepton charge by 2 units. And we have ways to ask nature by looking at certain processes that violate lepton number. And the prime example is this neutrinoless double beta decay. Basically, 2 neutrons inside the nucleus convert into 2 protons and 2 electrons. And that's something like the quark level, du, the simplest thing, again, if there is only a dimension 5 operator, this is the electron, you exchange a Majorana neutrino, with nu bar, annihilate each other. This is M of the neutrino, this Majorana mass. And so you would violate lepton number by 2 units. And here, I don't know if this you may have seen it, but in concrete, how you build this dimension 5 operator, it's that in full glory with L transposed. So you make 2 singlet under the SU2 with the epsilon, right? And then you insert the charge conjugation to make it singlet under Lorentz. So this is a trick. Are you familiar? I mean, whenever I have two doublets like L and phi under SU2, there's 2 ways to make an invariant. One is to do the bar, or dagger, U dagger U, and the other is I multiply them by epsilon. So I put an epsilon, which is the I sigma 2 in between. The intuitive way, remember how out of 2 spin 1/2 particle, I can make a singlet by antisymmetrizing. 1 down minus, that's exactly what it is doing. This is the celebrated seesaw. If I assume that the coefficient is order 1, again, this is a big assumption. I now plug in the VEV of the Higgs, the neutrino mass will come out V squared over lambda. And so if I insist that the coefficient is 1, lambda, it points to a very high scale. But of course, it's a big assumption to assume that the coefficient is order 1. It so works out in certain models, but it's not universal. Okay, yeah. And here's the concrete way. Again, this is over and over the same die. The simplest thing, I encourage you to work out this one diagram. It's a 3-level matching condition. And you get this particular model, the exchange of right-handed neutrino, you get the coefficient in front in terms of the product of couplings and the inverse of the mass. It's dimension 5, the mass goes downstairs. Great. Almost on time, actually. So let's take a glimpse at dimension 6. There's 59 structures. If you forget about the family indices, you can write down 59 structures. If you put the family indices, you get to 2,499. I never checked that, but it works. Many people have checked. And now you have a variety of vertices, right? This 3-gauge boson, no stuff with no fermions, with 2 fermions, with 4 fermions, and so on, and a variety of processes that you can look at, baryon number violation, as I said, all sorts of things. And very importantly, as you've probably heard, this is a serious, we take the field theory aspect of this effective field theory seriously. It's a full-fledged quantum field theory. If you work consistently to a leading order, to a given order, it's renormalizable. Yes, you have to renormalize many couplings, but it's renormalizable. And again, if you're interested in accuracy at a given order, it's fine, you work with it. So loops level, loops, anomalous dimension are known, and they're starting to be implemented in the phenomenology. So that's great, and I'm sure some of you are working on that. And then I want to finish with one thing. I know this is a bit controversial. So if I look, I work mostly on low energy probes. So this lepton family violation, CP violation, and you can play the game and ask, what is the scale we are probing, right? You compare your operator, your observable, and you have to make an assumption about the numerator, right? What's upstairs, and you assume it's order 1. But anyway, if then you get an effective scale. It doesn't necessarily mean it's the mass scale of new physics, but you get an effective scale. Basically, I just want to make sure about this. If you're looking at dimension 6 operator, what I'm going to show later, you're sensitive to lambda over square root of c, right? That's what I'm plotting, and I'm done. Here's what you get. So it looks like, so let me walk you through some of this. Yeah, this proton decay and neutrino mass, so double beta decay and lepton number violator, they're sensitive to the highest scale here. It's an accident of where we are with the experimental sensitivity, right? So these numbers are not purely theoretical. To work out these numbers, this order of magnitude, you need to know what the experimental sensitivity is, right? Next in line are the flavor change in neutral current in the lepton and quark sector in the electric dipole moments. They're about the PeV, 10 to the 3 TeV or more. And then so this, you see, up here are the ones that are forbidden, essentially, in the standard model. Very rare or forbidden. And then down here, G-2, all the charge current, all the stuff at the LHC, all the neutral current, parity violation, and low energy, they're probing lambda of the order 10 TeV. And so this you can easily understand, because these are not forbidden in the standard model. That one you can easily understand, because it's really the relative effect goes like V over lambda squared, and you have to compare this relative shift to the current precision, which is at 0.1% level. So you do the math, you get roughly 10 TeV at most. Okay, and I wanted to just show, but however, the positive message is that there's a lot of ways we are poking new physics beyond the standard model. I hope it convinced you.